Welcome to the final sub-module on survey tools and technology. At the end of this sub-module, you should be able to describe the commonly used surveying tools, state when each is most effective, and explain their similarities and differences. The development of magnetic single-shot and multi-shot tools introduced azimuth measurement alongside inclination. These tools contained 4 basic sections: a battery pack, a camera, an angle compass unit, and a watch. The single-shot system used a film camera to photograph a compass and inclinometer reading at a specific moment, usually after a survey station pause. Multi-shot tools repeated this process at intervals, creating a series of photographic records downhole. This provided both inclination and azimuth, a significant leap forward compared to inclination-only devices. The advantage of MSS/MMS was improved accuracy and the ability to track well trajectory in 3 dimensions. Their limitations were that they still required retrieval and film development, so data was delayed, and they were susceptible to magnetic interference from the drill string. As with all magnetic tools, correct placement in non-magnetic collars was essential. Despite these issues, MSS and MMS remained industry standards for decades and still find use in some environments. They were the stepping stone to electronic multi-shots and MWD systems, which removed film delays and provided near real-time data. These tools marked the beginning of practical 3D surveying in oilfield drilling. MWD revolutionized directional drilling by providing real-time survey data without interrupting operations. These tools use triaxial magnetometers and inclinometers to measure inclination, azimuth, and tool face continuously. The data is encoded and transmitted to the surface via mud pulse, electromagnetic, EM, or wired pipe telemetry. On the surface, decoding equipment interprets the signals and displays inclination and azimuth to the driller. In addition to survey data, MWD tools can also transmit downhole pressure, temperature, and vibration measurements, providing operators with vital insights into drilling performance. MWD tools can be collar-mounted, running continuously as part of the BHA or retrievable, allowing recovery for maintenance or redeployment. The key advantages of MWD are reduced survey time, continuous directional control, and integration with geosteering and logging while drilling LWD. Limitations include dependence on mud properties for mud pulse systems, limited bandwidth, typically less than 12 bits per second, and susceptibility to magnetic interference. Nonetheless, MWD has become the industry standard for directional drilling, rendering older systems, such as single shots and steering tools, largely obsolete. Its introduction transformed drilling from an episodic survey check approach to a real-time navigation process, enabling the complex well profiles we now take for granted. MWD tools can transmit data via several telemetry methods, each with strengths and weaknesses. Mud pulse telemetry is the most common, transmitting by modulating pressure pulses in the drilling fluid. It is reliable but relatively slow, typically 0.5 to 1.5 bits per second for pulses and up to 24 bits per second for a continuous carrier wave. Electromagnetic telemetry sends signals directly through the formation, independent of the mud system. It can achieve higher rates, up to approximately 12 bits per second, and is particularly useful in air or foam drilling, but suffers in deep or conductive formations. Wired drill pipe telemetry offers the highest bandwidth, exceeding 56 kilobits per second, using inductive couplers at each tool joint. This enables transmission of large datasets, including real-time logs and images. However, it requires specialized drill pipe and is expensive. The major benefit is in deep water applications where the rig rate is very high. Any time saved from higher data rates can be significant, incentivizing continuous use. The electronic multi-shot EMS tool improved on film-based MSS/MMS by digitizing the process. It contains magnetometers and accelerometers similar to those in MWD and steering tools, but is battery-powered and memory-based. Before deployment, the tool is programmed at the surface to take shots at predetermined time intervals. While drilling, it records inclination, azimuth, and tool face, storing the data in onboard memory. Once retrieved, the tool is downloaded and the data is correlated against surface depth logs to produce a survey record. The advantages of EMS include eliminating the need for film development, providing more accurate digital measurements, and enabling the collection of multiple survey stations in a single run. Its main drawback is that it is not real-time. Data is only available after retrieval. Therefore, EMS is best used in environments where cost control is key and real-time steering is not required. It remains popular for lower budget or simple wells, or as a backup when MWD is unavailable. EMS demonstrates how digital technology streamlines survey processes, eliminating film while preserving affordability. It represents a middle ground between old-style single shots and fully real-time MWD systems. Gyroscopic survey tools address one of the primary challenges of magnetic surveys, interference from steel and local magnetic anomalies. Because gyros reference Earth's rotation rather than the magnetic field, they provide accurate azimuth regardless of surrounding conditions. This makes them the tool of choice inside casing, in high inclination sidetracks, or near magnetic interference zones. Early gyros were free gyros, utilizing film-based recording, which was later replaced by rate gyros and more advanced north-seeking gyros, NSG, and inertial navigation systems, INS. Modern gyros often use MEMS technology, making them smaller, cheaper, and more rugged. The trend is toward optical or laser ring gyros, offering even higher accuracy and robustness. The main limitation of gyros has historically been cost and complexity, but these are falling rapidly. Gyros are now routinely deployed for critical anti-collision surveys, casing exits, and environments where magnetic data is unreliable. Their independence from magnetics makes them indispensable in modern directional drilling, especially in anti-collision situations near the surface where the casing of nearby wells causes magnetic interference. In short, gyros provide the accuracy standard against which other survey tools are measured, ensuring safe, precise wellbore navigation in challenging conditions. The picture to the right is an example of a free gyro multi-shot system, one of the earliest gyro-based survey technologies. These tools used a spinning gyroscope to establish a stable reference independent of Earth's magnetic field. Film cameras recorded the readings much like early magnetic multi-shots. While groundbreaking for their time, free gyros were bulky, expensive, and labor-intensive. Film development introduced delays, and the mechanical gyros were prone to drift if left running too long without recalibration. Nevertheless, they offered a crucial advantage: the ability to survey inside casing or in areas of severe magnetic interference where magnetic tools failed. Free gyros marked the beginning of azimuth independence from magnetics, paving the way for more advanced electronic and north-seeking systems. Their use today is rare, but they remain a milestone in drilling technology. The picture on the bottom right shows a dynamically tuned north-seeking gyro, NSG, an evolution beyond free gyros. Unlike earlier film-based systems, north-seeking gyros are fully electronic and capable of automatically aligning with Earth's rotational axis to determine azimuth. By eliminating film and mechanical drift issues, they provide continuous, highly accurate data. NSGs are smaller, more rugged, and easier to deploy, making them popular for cased hole surveys, sidetracks, and anti-collision verification. They can run memory-based or with surface readout, depending on well needs. Companies like Gyrodata pioneered this technology, helping bring gyro surveys into mainstream use. The key benefit is that north-seeking gyros are immune to magnetic interference, which means they can provide reliable azimuth readings in environments where magnetic fields are present. Their accuracy also makes them the reference standard when validating MWD data. The main drawbacks are cost and power requirements, but these are steadily decreasing. Ring gyro inertial navigation systems bring aerospace technology into drilling. Tools like Baker Hughes's rig system were adapted from flight control gyros, which were initially used in the Harrier jump jet. These systems used laser or ring gyros to establish orientation, combining gyroscopes with accelerometers to provide continuous position tracking. The advantage of inertial navigation systems is unmatched accuracy and independence from both magnetics and external references. They can measure inclination, azimuth, and positional displacement with extreme precision, making them ideal for complex or extended reach wells. However, the downsides were significant. Early tools were bulky, often more than 5 inches in diameter, expensive, and required rare components. With the end of Harrier production, parts became scarce, limiting adoption. Despite these drawbacks, inertial navigation system technology demonstrated what was possible: continuous, high-accuracy surveying in real time. Today, inertial navigation systems are re-emerging in smaller, cost-effective packages that utilize MEMS and optical technologies. They may soon dominate the market as cost comes down. The lesson from the ring gyro is that advanced inertial navigation can deliver aviation-grade accuracy to drilling, enabling wells with tighter tolerances and safer anti-collision assurance. Ring laser gyros are a form of optical rotation sensor and, unlike the preceding mechanical rotor systems, contain no moving parts in their simplest form. Within the sensor, which contains a machined quartz block, 2 laser beams are formed, one moving clockwise and the other counterclockwise, around an enclosed polygonal optical path loop with 3, 4, or more sides and mirrors at the vertices. These laser beams interfere with each other, creating a standing wave diffraction pattern observed by a photodetector located at one of the vertex mirrors. This is a little like dropping 2 stones into a still pond, where the waves from each stone meet and form a pattern of waves with even higher peaks and lower troughs, where they cancel out. If the device is rotated, one beam experiences a shift up in frequency, whilst the other experiences a shift down, causing the interference pattern to move. As the device rotates, the vertex photodetector counts the fringes, thereby measuring the rotation of the sensor. This relativistic phenomenon is known as the Sagnac effect, after G. Sagnac, who demonstrated and recognized the condition whilst conducting experiments to detect the effect of the relative motion of the ether in 1913. In a surface readout gyro, a downhole electronics package replaces the camera angle unit and timer. A wire line supplies power and connects the probe with a surface computer that monitors probe performance and prints survey data as it is gathered. Accelerometers are used to measure hole inclination. However, the system still relies on conventional 2-degree of freedom gyros for directional data. Problems with battery-powered mechanical cameras are eliminated, and survey data are supplied in real time. The surface computer can monitor probe performance. Therefore, time wasted by misruns is reduced. Recent advances in MEMS gyros and gyro-while drilling (GWD) systems are gradually replacing surface readout gyros, as they provide the same benefits with less operational complexity. Still, surface readout gyros remain valuable when wireline support is available and when high-accuracy gyro data is required on demand. They bridge the gap between old-style film gyros and modern MEMS-based systems, showing how digitization streamlined survey processes, improved accuracy, and made gyro surveying more practical and reliable. This summary slide compares the accuracy and acquisition rates of different survey tools. At the low end, inclination-only tools like Totco or Anderdrift are inexpensive but limited, suitable only for verticality checks. Magnetic single shots and multi-shots add azimuth capability, but suffer from interference and delayed results. Electronic multi-shot tools improve accuracy with digital storage, but still lack real-time data. MWD systems represent the industry standard, offering continuous surveys, real-time feedback, and integration with logging while drilling, but they remain vulnerable to magnetic errors unless supported by non-magnetic collars. Gyro tools, particularly modern north-seeking gyros and MEMS-based systems, offer high accuracy, azimuth independent of magnetic fields, making them ideal for anti-collision and casing applications, albeit at a higher cost. Inertial navigation systems represent the cutting edge, combining gyros and accelerometers for unmatched accuracy and continuous positioning, though cost and size limit widespread adoption. The key message is that survey technology spans a spectrum from cheap and simple to advanced and expensive. The right choice depends on well objectives, required accuracy, and budget. Ultimately, the industry balances cost, precision, and efficiency to choose the most appropriate survey solution for each operation. This chart is only for relative comparison of the accuracy of the various survey tools. The other acronyms are CNSG, Casing North-Seeking Gyro SUCOP, Survey Corrected for Drill String Interference. This is software developed by Shell. DMAG, Survey Corrected for Drill String Interference. This is software developed by SLB. GMAG, Survey Corrected for Drill String Interference and Crustal Field. This will be discussed later in the course. As we conclude, let's revisit the objectives of the whole module. You should now be able to list the various types of surveying tools used in directional drilling, from inclination-only devices like Topco through magnetic multishots and EMS, up to modern MWD, gyro, and inertial navigation systems. You should also be able to identify the sources of magnetic survey errors, drill string interference, magnetic variance, and crustal field anomalies, and explain why drill string interference accounts for most of the inaccuracies. We then explored how to calculate non-magnetic component requirements for a directional BHA, ensuring survey tools are shielded from magnetic distortion by sufficient non-magnetic drill collars. Finally, you should now be able to describe the commonly used survey tools, explain when each is most appropriate, and outline their similarities and differences. The overall message is that survey technology underpins directional drilling success. Without accurate surveys, well placement, anti-collision assurance, and reservoir navigation are impossible. With the right tools and careful error management, we can drill complex well profiles safely and efficiently. This is why survey knowledge is fundamental to every directional driller and engineer. That brings us to the end of the Survey Tools and Technology module. We've covered the journey from simple inclination-only devices to sophisticated MEMS-based gyros and inertial navigation systems. Thank you for your attention and engagement during this module. Please progress to the quiz before we continue on the journey.